So if you remember from last time, I said there are mainly two parts in this lesson. One is finding or calculating the magnetic field created by different conducting objects. And the other thing is finding the magnetic force. So we mainly did this part last time, magnetic force. And today we are going to do how to find the magnetic field created by different current carrying objects. Okay. So before going into equations, let's go through how to find the direction of magnetic fields created by currents. So here also we use something called the right-hand rule, but it is different from what we used for force. In fact, this is the easy one. Okay, this is easier than the right-hand rule we used for force. So in this one, the main components of your right-hand rule are your thumb and the set of other fingers, other four fingers. So you can use your thumb to represent current. If you do that, this other set of fingers will bend towards the B field. Or you can even use your thumb, you can use the other set of fingers to represent current. If you do that, your thumb will tell you the direction of the B field. In other words, you can interchange between the two. So you can either use thumb to show current, or you can use the set of other fingers to show current. Whatever left after you choose to show current will show the B field. Okay, so here are some examples. This is a very easy law. So let's look at this one. Okay, here we have a current carrying conductor. Let's say it is a wire, long wire which carries current upwards. So to find the B field created by that, the easy way to do it is keeping your thumb along the current. That's easier to do, right? Because current is going along a straight path. My thumb is also something straight. So you keep your thumb along the current and the fingers curl in the direction of your B field. So can you see that your B field is going around a circle like this? So if this is a straight line, okay? Your B field will be something like this, which carries current in the counterclockwise direction, like in loops. Okay. So when you have a object like this, it is easy to use your thumb to show the current. Okay, here we have a loop. In this one, can you see that the direction of current changes from place to place? Because it's a circle, right? So you can do the same thing that we did here. So that's what I have done here. See, my thumb is facing this way and these are my fingers. So you can see that your B field is something like this. It comes out from inside and then goes like this. Can you see the? Yes, so it is inside, your B field comes out, and outside your fingers curl inside, right? So it goes into the plane from outside. So this is one way to do it. But for this, you will have to take your hand all around the loop. Very inconvenient, right? So another way, the easy way to do this is so this is current. Curl your fingers, use the other 4 fingers, do this. So curl your fingers around the current. So I'm using my other 4 fingers along the direction of current. I'm bending them along the direction of current. And my thumb is now pointing upwards. So it shows the direction of the B field inside the loop. So inside the loop, if it's coming outside, it should go in, right? Because it's like in circles. B field is like in circles here. Okay, so the third one. So the third example here is a solenoid. So solenoid is something like a spring where you have where a wire which carries current is kind of coiled around something. So it's like a spring. So can you see that current goes like this through every loop? From this loop, it goes like this and come again from underneath and goes like this. So if you are going to use the right hand rule to this one, this way is going to be very hard. Like this way means if you keep your thumb around the current, it's going to be very hard, right? How many loops are there? And how many times you will have to go around the loop? It's not easy. So the easy method is, again, bend your fingers along the current. So current is flowing this way, right? Like this. Like this. So bend your fingers like that, and then your thumb will give the direction of the B field. So you can see that the B field inside the solenoid is this way. In this one. Thumb is pointing this way, see? So this is like, I think the first lecture that you did in B fields. So they talked about this right hand rule. So this is the easy right hand rule. Okay, so this is about the direction. Now let's actually go and see the equations. So there are only few equations that you have to know. You have to know how to find, you have to know wires, and also you have to know solenoids. That's all you have to know. So in this slide, we are going to look at wires. So assume that this is a very long wire, okay? We know how to find the direction created by this wire using right hand rule. We keep our hand like this, thumb along current, and these fingers will tell you the direction of the B field. So your B field is something like this. So this equation gives you the B field at a point R. So this is the distance away from your current, R away from your current. So let's say I want to find the B field here at this location at A. So what should we do? We should have this distance. This will be my R then. So this is the distance from the wire. So always this R is the perpendicular distance from the wire, from your current. Okay. You shouldn't take a distance like this. So some distance like this is wrong. Always the perpendicular distance, because this is a very long wire. So you can draw a perpendicular from any point, right, to the wire. So this R is the distance, and mu naught, we have this constant mu naught. It is called the permeability of free space. So in electric fields, you might remember that we had something called epsilon naught, permittivity of free space. So in the same way, For magnetic fields, we have this constant. It is the permeability. This is permittivity. This is permeability. And it is given by this value. And it is a constant. Okay. So today we are not going to derive these equations. We are just going to use these equations. And on Monday, we will try to derive these using something called Ampere's law. So on Monday, next Monday, we will do Ampere's law. It is a little hard part. But for today, just knowing the equations would be enough. Okay? Okay. So I have a few different levels of problems. So these are two easy problems from the equation, from this equation. Try to do it and tell me the answers. So the first one, magnetic field produced by a long straight wire. So they're talking about this equation. We know B is proportional to current. That means B increases when we increase the current. And B decreases when we increase the radius or the distance. So proportional, inversely proportional. Your answer is B. Second one, at double the distance from a long current carrying wire, the strength of the magnetic field. So this is the first equation, first scenario where you don't do anything. And the second case is when you double the distance. So now your distance is not r, it is 2r. Mu naught I divided by 2 pi r. This is your old B, and you have a 2 here, right? You have, what's wrong with this? Okay, so you have a half here. So the new magnetic field is half of the original value. So this is half. Okay. So this was easy, right? So this was just getting familiar with the equation. So here are two problems. The first one is a little hard. So for this, you will need what we learned on Monday as well about magnetic force. So try to do it and tell me the answer. So a wire lying in the plane of the page carries a current towards the bottom of the page. So although I'm drawing like this, we are talking about a scenario on paper, right? So something like this, horizontally. So you draw a line towards you in the paper. Okay. What is the direction of the magnetic force it produces on an electron that is moving perpendicularly towards the wire, also in the plane of the page from your right? Okay, now this is an electron, and this electron is coming towards the wire. So this is a current carrying conductor. Okay, so to find the force on the electron, we need to find the magnetic field at this location, right? We know this current carrying wire will produce a magnetic field at this location. So what we are going to do is, first we are going to apply right hand rule to find the direction of the B field here. Okay, so here is my hand and the current is going down. My hand is flipped, right? So you can use your hand and see. So when I do that, from this side, current, my fingers are coming out of the page. So something like, I can't use my left hand. So I'm flipped, okay? So this is down. So this is the correct side. So here my fingers are pointing outwards. So my fingers were pointing outwards. That means the B field is pointed out of the page. Okay, out of the page. So are you okay with the direction of the B field? So this is not what they're asking in the problem. They're asking about the magnetic force. Are you okay with the B field? This is the direction of the B field. So try it and tell me if you're okay with it. Are you okay with the B field? No answers? Yeah, okay. So we know the B field. Now we can find the force, the direction of force on this electron. But before going into this, let me give you a small summary of that. Force on charges, moving charges. So when you apply right hand rule to a charge, if your charge is positive, the direction of force is same as the right hand rule, right? Same as the direction given by the right hand rule. If your force is negative, sorry, if your charge is a negative charge, you have to flip it. Remember, flip it means you flip the direction you get from the right hand rule. So here we have a negative charge, right? It is an electron. Okay, now I'm going to apply the right hand rule. Do you remember it? For force, the right hand rule is you keep your fingers, okay, you keep your fingers along the direction your electron or the charge moves. Okay, so this is my left hand. So it moves this way, right? So you can use your hands. I'll be flipped, okay? So this is my left hand. So electron is moving this way. And my B field is towards myself, out of the plane. Yes? Yeah. So can you see my finger is pointing upwards? So from the right hand rule, what I got was up. But we know that is correct for a positive charge. If our charge is a negative charge, we have to flip it. That means since our charge is a negative charge, which is an electron, the direction is not up, it is down. So this one, towards the bottom of the page. Okay, I got a question. Why are my fingers pointing left if the current is pointing downward? So these are two different things. Okay. So the okay, let me explain it again. So what is happening is you have this current carrying conductor. Okay. And this current carrying conductor creates a magnetic field at this location. Okay, created by I. So this magnetic field was created by this current carrying conductor. So for that, we use the right hand rule we learned today. So here is my thumb pointing downwards, and the magnetic field produced is given by this direction. Okay, so that is one part of the problem. Find the direction of B field. created by I. Okay. So the second part of the problem is now you have the B field. Now you can find the force it will give to this electron. Force on electron. So now we have an electron moving this way in a magnetic field. So this is the second part of the problem. So they are asking, what is this? What is the direction of this force? Okay. So that is why my fingers was pointing this way towards left, because so now I am applying the right hand rule to find the force. So my fingers are pointing leftwards because that is the direction where my electron moves. Okay, so I think we are good. So the answer is E. So these type of problems are very confusing and they are very common. They're very common, but they're very confusing. So do this in different ways you can. Maybe you can draw currents this way and keep positive charge here, make it move the other way, and try to find the force. Okay? So you can create your own problems and try it. That is how we make problems for quizzes sometimes. We get a problem, change it a little bit, and give it to you. Okay. So the next one, how much current must flow for 10 to the negative 3 Tesla magnetic field to be present 1 centimeter away from a wire? Okay, let's say we have a wire and it is 1 centimeters away and they have given the B field. So it is a easy substitution, right? Mu naught I divided by 2 pi r. They are asking us to find the current. If I make current the subject of the equation, I get this equation. So I'm substituting the values. 1 centimeter is 1 times 10 to the negative 2. Mu naught is 4 pi 10 to the negative 7. So when we do this, we get the answer 50. So are we okay? Yes? Okay, let's move to the next part. So here are 3 problems. They are similar, but as the first step, I want you to do the first one and tell me the answer. Okay? Okay, so I'll explain it. So if you got the answer D, I think you know how to do it. You can continue with the other 2. I will do the first one. So you have 2 parallel wires, identical currents, and it's coming towards you. So when we get problems like this, what I usually like to do is I draw one of the wires in one side, it is away from the problem, and then I mark the B field around it. So here the current is going down, right, towards the bottom of the page. So if I apply the right hand rule, my thumb is pointing downwards and my fingers are coming out of the plane from this side and going into the plane from this side. So do you get this when you apply right hand rule? Okay. So I have that for reference. Now I have 2 of those here, right? I have 2 of such wires here. So we need to find the magnetic field right in the middle. Okay, now what I'm going to do is I'm going to compare this wire and this position to this reference diagram. So this point, let me say this is midpoint M. This midpoint is at the right side of the first wire, right? At the right side of the first wire. So can you see at the right side of the wire, it is coming out of the plane. Your B field is coming out of the plane. So from the first wire, your B field is coming out. Now let's go to the second wire. Point M, this midpoint, is at the left hand side of the second wire. Can you see that it's at the left hand side? So here is my reference diagram. So we know at the left hand side, it is going into the plane. So from the first wire, the B field is coming out of the plane, and from the second wire into the plane. And they are exactly equal. Why are they exactly equal? Same distance, it's the midpoint. And what else? They have the same current. So they cancel off, right? So I thought the current would be point out of the page. Because that is true, that is true. So I can't draw something horizontal in the page, right? So I can't draw this in the page. So this is your page and you will be drawing lines like this. Your B field is coming out of the page and into the page. So they cancel off. Okay. Okay. So B is the correct answer. Let's see. So there are two wires. This is actually on, so you have to draw it on the page, okay? So on the page, wire to your right carries current towards you and wire to your left carries current away from you. From your point of view, the magnetic field at the point exactly in the middle. Okay, so here we have two wires carrying current on opposite directions, right? So we have a reference diagram for this case. Let's draw a reference diagram for this one going up. So for a current going upwards, it is like this, right? Towards the right hand side, it is this way. Towards the left hand side, it is coming out. So now I'm going to look at my reference diagrams and mark the currents, or mark the B fields. So this is the first wire, second wire. So from the first wire, this point is towards the right. So it is this way towards the right into the plane, right? Or if you think of your page like this, downwards. So this is from the first wire. From the second wire, this point is towards your left hand side. So this is the reference diagram. So towards the left, it is also going into the plane, right? So from both of them, from both of the wires at the midpoint, the B field was into the plane. In other words, if you look at the paper, it is down, right? Going down. So your answers are, so they add up. Your answer is B. Points down. So what is the answer you got for C? I'm going to draw the C, two parallel wires. So they are opposite to each other. So I'll draw the same thing as the previous one, same directions. So they are talking about a point like this, right? 20 centimeters from the first wire and 60 centimeters from the second wire. So it is a point like this. Okay, now that we know the point of interest, let's find the direction of B field from each of the wires. So from the first wire, what's the reference diagram that I have to do? This one, right? So this point is towards the left. So towards the left, out of the page, right? So out of the page, sorry, here, B1 is out of the page. And from the second wire, current is going down and this point is towards the left. It is going in. So this was B1. B1 was coming out of the plane and B2 was going into the plane. So the total B field is the addition of the two, but they are in opposite directions, right? So B fields are vectors. So if we consider out of the page as positive, your total B field will be B1 minus B2 because they are opposite to each other. Mu naught I over 2 pi R1 minus mu naught I over 2 pi R2. So I'm going to substitute the values at the end. Mu naught I, 2 pi R common. So I'll take them out. So I get R1. What is R1? Minus 1 over R2. So if I substitute the values, I get 4 pi 10 to the negative 7. I is 10. 2 pi. R1 is 20 centimeters. So I'll substitute it in meters. R2 is 60 centimeters. So when you do that, you should get the answer 6.7, 10 to the negative 6 Tesla. Again, the answer is B. So this is the next one. So this is not in your worksheet. So I just wanted to go through some theory part using an example. So this is very similar to what we did initially with that wire and the electron. Remember, I was asking you to find the force on the electron due to a current carrying wire. Okay, so this is a very similar one, but here we have two wires. Okay, so I'm just going through this, and this is a very extremely common example that they ask in the exams. So here are two wires carrying different currents. They can be equal or different, we don't care, but they are carrying currents. So we know when there are current carrying conductors, each conductor, each wire will have a magnetic field around it, right? So in this example, I have drawn the magnetic field of the first wire. So in the same way, the second wire will also create a magnetic field around it. So for now, let's only focus on this one, the magnetic field created by the first one. So due to this magnetic field, this wire is going to feel the force, right? So this wire, the first one, created this magnetic field. And this second wire is a current carrying conductor in a magnetic field now. So it is going to feel a force. So in this example, what we are going to do is we are going to find the force that the second wire is going to feel. Okay. So the first part of the problem, find the B field created by the first wire at the location of the second wire. So we know B field created by a wire is given by mu naught I divided by 2 pi distance, right? So the second wire is d away from the first wire. So your distance is d. So this is the B field created by the first wire, B1. Okay. Now the second part is, what is the direction? Let's find the direction at the end. Can you tell me the magnitude of force? Do you remember the equation for force? So I will write that. You all are going to tell me, okay? So can you try to apply this equation and try to find the force on the second wire? So what do you get? So F2 is the force on the second wire. We know for this, we need the current of the second wire, which is I2, length of the second wire. So they are talking about this length, right? L2. L2. The B field at the second wire. So at this location, what is the B field? We just found it, right? This one. It is created by the first wire. Mu naught. Sorry, this is I1. I1 divided by 2 pi d. Why I1? Because it was created by the first wire, right? Okay. Now the problem is, what is theta? What should be your theta? So theta is the angle between the current and the B field. Very good. It is 90. So why? So this is your I2. So this one is your I2. It is going upwards. At this location, your B field is into the plane, right? See, at this location, it is into the plane. So into the plane and upwards. That is a 90 degree. Something like this. This is upwards, current is upwards. And this is into the plane. See, into the plane. So your theta is 90. So when we simplify this, we get, if I write it nicely, mu naught I1 I2 divided by 2 pi d times L2. So usually, like I said before, these wires are infinitely long. These are very long wires. So when they are finding the force, they will usually tell you force on this much length, force on this small length. Okay, so these are actually very long wires. If they want the force, they will tell you the length that they want. Okay, now can you find the direction on this wire? Force, the direction of force on this wire. Where should it be? So I'm also going to apply the right hand rule. So your fingers, so the force right hand rule is you point your fingers along the current, so they're upwards. Okay, and this is my left hand, this is the right hand, upwards, and then I curl my fingers towards the B field. Can you see my finger is pointing left? So my force is this way. Force on the second one is this way. Okay. So if we repeat the same thing that we did now for the other wire. Okay, if we repeat the same thing for the other wire, what we will get is, we will get a force this way. And also we will get a similar equation. L1. Similar equation, we will exactly get the same equation. So if the length that you are going to consider is the same, you will see that these forces are exactly same. No matter they carry different currents, the force acting on each other will be the same. Okay. So I have a summary in the next slide. So this is the summary. So if you have two wires carrying currents in the same direction, okay, two wires carrying current in the same direction, then they will attract each other. We can find these just like we did the previous example. Okay, they will attract each other. And if you have two wires carrying currents opposite to each other, they will repel each other. Okay, this is like very different from what we have learned, right? Here equal attract and opposites repel. And this force on each other is an action-reaction pair. They are like an action-reaction pair. They are equal and opposite. Okay, can you see? Here, although it's an attraction, they are equal and opposite. Although here it's a repulsion, equal and opposite. And whether you have the same current or a different current, always you get this relationship. The forces are equal. And the force is given by this equation. Here I have written the force per unit length. So instead of having, you can even remember it like this. I1, I2, 2 pi d times L. Length is the length that they are going to talk about. So if they ask you to find the force on a tiny length like this, you multiply by this length. Okay. So this is an equation that you have to know. At least you have to know how to derive this. We combined force equation and the B field equation. Okay. So here are two problems. And I want you to do this and tell me the answers. They are very easy. So your answers are correct. Let me quickly do it. So two long parallel wires carry equal currents. They haven't said anything about the direction, right? So we don't care about that. They're only talking about the magnitude. We know force is given by this equation. Mu naught I1 I2 divided by 2 pi d times the length that we are considering. So what are they doing? They are saying the wires have the same currents. So instead of I1 and I2, I will write I and I because they have the same current. I'll have I and I. So they, what's wrong? Sorry. So they double the current, right? So if nu is mu naught 2 times I, 2 times I. So each wire has double the current now. 2I, 2I, 2 pi d over times L. So if I take these 2's out, 2 times 2 is 4. And I'm left with this part. I 2 pi d times L. So this is same as our old force, right? This one. That means when you double the current in each wire, your force is 4 times the old value. So the second one, 2 long parallel wires carry currents 5 amps and 8 amps in the opposite direction. So if this is taking current this way, the other wire takes current this way. We know if the currents are in opposite direction, it is a repulsion, right? That is something that you have to know. Because when in exams, it's hard to do every time you get a question, right? It's so hard to do the right hand rule all the time. So just remember this. So it's a repulsion. And now let's find the force per unit length. So they're asking F over L. Mu naught I1 I2 over 2 pi d. Mu naught is 4 pi 10 to the negative 7. I1 is 5, I2 is 8. 2 pi, the distance is 0.3. So when you simplify this, I think you should get the answer A. So are we okay? Okay. So I will move to the next part. So the last equation that you have to know is to find the magnetic field inside the solenoid. Although this diagram looks hard, it is the easiest one. Okay. Solenoid is something which is like a spring. Think of a wire like this, which has a lot of turns. Okay. And it carries current. So according to this diagram, can you see that your current is going like this? So these loops that I'm going to mark have current this way, these parts of the loops. So if I apply right hand rule, my fingers are pointing along the currents this way. And my thumb is going to give me the magnetic field. So this is your B field. It is going this way. And something to remember about solenoids is B field inside is given by this equation, which I will talk about in few seconds. But the B field outside the solenoid is 0. Okay. Outside the solenoid, the B field is 0. So you will learn about this when we go to the next part of the lesson. So there's something called the Ampere's law. Okay. But for now, like for multiple choice questions, just remember that B field outside a solenoid is 0 and inside is given by this equation. So it is inside. Okay. So this is a very easy equation. Mu naught, you know, it's the permeability of free space. I is the current through your solenoid. And N is the number of turns. So there are turns, right? Loops, circles. So it's the number of turns. And this L is the length of your solenoid. So what do you mean by the length? Length is this, okay? Not the actual length, not like you are going to stretch the spring and take the length, not that length. Okay, so this length. So in other words, this N over L quantity, N is the number of turns, right? Turns over length. So this really gives you the number of turns per unit length. It's the number of turns per unit length. Why am I talking about this separately? Because sometimes in problems, instead of giving N and L separately, they directly give you, this is the number of turns per unit length. So directly give you N over L. Okay. So this is very easy. So here I have a question, just a substitution. Let's try to do it. So here I have a solenoid. It carries current and it is 20 centimeters long. And also they have given the number of turns as 5,000. The current is 10 amps. So we can easily find the B field inside the solenoid. See, they're talking about at the center of the solenoid. So they are talking about inside, right? So B is given by mu naught I N over L. Now I'm going to substitute. Mu naught is 4 pi 10 to the negative 7. Current is 10. N is 5,000. L is 20 centimeters. I have converted this to meters. So when you do that, what's the answer you get? Do you get C or E? E, right? Yeah. So the answer is 0.32 Tesla.